Hi everyone, just a little update before we get started with the episode. Dan and I have decided that we're going to try putting out episodes every other week instead of every week from now on. We decided to do this so that we could spend more time on each episode and make sure that we're bringing you the best quality thing that we can make, given our busy schedules and the fact that we're just doing this on the side because we enjoy it and we have, full-time jobs otherwise. So we will continue to make consistent episodes just posted every other Monday. So thank you for your support and for sticking around, and let's get started with today's episode. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
Hey, Dan.
Hey, Shalma. What's been going on?
Well, I moved into my new apartment in New York. Pretty exciting.
Awesome.
Yeah, although something strange actually has happened.
Okay, what's that?
Slightly strange, which is that there are some new dishes in the pantry that I've never seen before, and I definitely didn't put them there, so I don't know how they appeared.
Okay.
And so I have two working theories right now, and I think they're both pretty good, and it's hard for me to decide which one's probably right. So the first one is that there is a reverse plate thief in the neighborhood.
A reverse plate thief? Is that what you said?
Yeah. Like I'm new to this neighborhood, so maybe there's someone in the neighborhood who's, breaking into homes, leaving plates, stealing nothing else. Maybe that just happens here, in which case it totally makes sense that I would find these new dishes.
Okay, I'll try to be open-minded. What's your second theory?
And my second theory is that one of my roommates bought them and didn't tell me.
Okay, well, that seems a bit more likely than the reverse plate thief, doesn't it?
Well, I don't know. They both predict my experience of having these new dishes pretty well. Like, how do you distinguish between those two theories if they both work?
Well, I agree, like both theories in principle agree with the data you have. But surely the theory involving your roommates is more sensible. I mean, it's at least more plausible with things we know about the universe. It explains without any new complicated features that can explain the data, unlike a reverse plate thief.
So you're saying because the reverse plate thief theory means that I would have to assume so much more, just like this neighborhood is so different from other neighborhoods that there's a reverse thief like that. Yeah. It makes it a worse theory.
Yeah, I would put it this way. Your second theory, the one involving your roommates, can explain more with less than the theory involving the hypothetical reverse plate thief.
I see. So as in, it takes a lot less to believe the roommate theory.
Yeah, the roommate theory involves elements you actually know exist. That helps.
So I guess the point here then is that this should also be true about scientific theories, right? Some are just more powerful than others, even if they predict the same things.
Yeah, physicists are always striving to discover theories that can explain as much as they can about our universe, while at the same time being as simple as possible.
Yeah, I suppose that makes sense. Do you have an example in mind, Dan?
Well, there are a lot of examples. One thing I've been thinking a lot about recently are things we call grand unified theories. These are theories where you take the three forces in the Standard Model, the electromagnetic force, the strong nuclear force, and the weak nuclear force, and explain them all in terms of one overarching principle or one grand unified force. These forces, when you first look at them, look totally unrelated, but it's possible they're actually facets of the same underlying thing, the same sort of underlying principle.
So you're saying that grand unified theories might be able to explain three forces in one.
And they do it without any reverse plate thieves.
Great. So in this episode, let's explore more about these grand unified theories, what they are, how they manage to turn three forces into just one, and what explanatory power they really have.
Sounds great. Let's get started.
Okay, so Dan, let's start by just talking about why you would want to do this in the first place. Why would you want to replace the electromagnetic force, the strong force, and the weak force, all perfectly good forces that we understand? Why would you want to replace this with one unified force to begin with?
Well, you might think that by replacing these three forces with another more complicated unified force or theory, that you'd just be trading one complicated thing for another complicated thing. But this doesn't have to be the case. To get a better perspective of what I'm talking about, let's look back to history. So there are two examples of really great efforts of unification that happened in the history of physics. The first has to do with gravity. So if you went back, before people like Galileo, and you asked around the top minds in physics and said, well, what causes things to fall towards the Earth? They would have told you something about gravity. Then you could have asked them, what causes planets to move in their orbits? And they would have said, well, something totally different. And they would have explained what they knew about that. It wasn't until, Galileo, followed by people like Newton, put together a universal theory of gravitation that we understood that these two very different seeming things turned out to be the same force of gravity. The idea that when objects with mass attract each other, that causes things to fall towards the Earth, and it causes planets to move in their elliptical orbits around the sun. All of this was really the same thing. So you could explain more with a simpler theory than you could before this idea.
Right. Instead of needing different forces for every situation, you can just use this one force of gravity and it explains all of those phenomena.
Exactly. And then the second historical example I want to mention has to do with electricity and magnetism. If you ask physicists in the early 1800s what they knew about electricity and what they knew about magnetism, they would have described a really good theory of electricity, and describe how static charges work and things like this. It would describe a lot of stuff they had observed. And then they would tell you about their theory of magnetism, which would explain how compasses, point north and things like this. And it would be a pretty good theory. But as far as they were concerned, the electric force and the magnetic force were totally different things, driven by different kinds of fields that didn't have any obvious connection. But by the middle of the century, James Clerk Maxwell and others sorted out that they're really just two sides of the same coin. All a magnetic field is a changing electric field. So there's not an electric field and a magnetic field. There's an electromagnetic field. It's one thing. And once you understood that, you could explain not only what people knew about electricity and magnetism, but a bunch of other stuff that they previously hadn't understood, including the nature of light and other phenomena in nature. Again, they could explain a lot more with a simpler theory. They could explain more with less.
Mm-hmm. Great. So it definitely is useful, as we can see, to make these unified theories, try to unify different phenomena into one explanation. But, these three forces we're talking about, they are very different, right? So why would we try to combine those?
In our current best theory of particle physics, what we call the standard model, there are these three forces: electromagnetism, the strong force, and the weak force, and they seem totally unrelated. They're communicated through space by different kinds of particles. They act on different kinds of particles for different kinds of reasons. They just don't seem to have anything to do with each other. But the standard model is a complicated theory. It doesn't explain all that much with very little. It explains a lot, but it does it at the expense of a lot of complexity. It has 19 different free parameters, and like I said, 3 different forces that don't seem to have anything to do with each other. Ideally, what we would want is some sort of single theory that could explain why these parameters have the sorts of values they do, why different forces have the different strengths they do, why they all have the different features. In other words, what we want is a grand unified theory that not only can describe the things we observe, but explain why they observe in the patterns we see in nature.
So if the electromagnetic force, the strong force, and the weak forces seem so different, what makes physicists think that they might all be part of the same force? Is this just a guess or wishful thinking, or just like we're hoping that we can find the unified force?
Well, there could be some wishful thinking going on here, but there are some pretty compelling hints that these forces might be connected in some deep way. I'd say the first really big historical hint of grand unification was the simple fact that electrons and protons have the same magnitude of electric charge. They have -1 and 1 for their electric charges. That didn't have to be true, Protons, after all, are made up of quarks, and electron is an example of a lepton. Quarks and leptons are totally different things according to the Standard Model. There's no reason to think they would have to have the same quantity of electric charge. So the fact that they do suggests that maybe the quarks and leptons aren't really entirely different like they seem to be in the Standard Model, but might be different states of the same underlying thing. So in the Standard Model, there are three forces, and each one is communicated by exchanging particles that pass back and forth through space. So in the electromagnetic force, for example, the reason that particles feel the electromagnetic force is that photons are moving back and forth between those charged particles. The weak force is mediated by particles that we call the W and Z bosons. These are kind of like heavy photon-like particles. But through interacting with one of these particles, it's actually possible for the kind of particle that's interacting to be transformed into a different kind of particle. Like an electron could be converted into a neutrino, or a neutrino could be converted into an electron. From the perspective of the weak force, electrons and neutrinos are kind of different states of the same underlying thing. They're different sides of the same coin, as I like to say. In a similar way, the gluon, which communicates the strong nuclear force, can change a quark with one color. A color is kind of like a charge, but the sort of thing the strong force feels, into a quark with a different color. So all those different kinds of quarks are really just different versions of the same thing. In a grand unified theory, we imagine that there's one big force that encompasses all of the forces of the Standard Model, and it can convert quarks into leptons and vice versa. So in other words, all of the kinds of particles that we think of as matter in our universe in a grand unified theory are really just different versions of the same underlying thing.
So when did people start thinking about these grand unified theories?
So I'd say the first real grand unified theory was proposed in 1974 by Howard Georgi and Sheldon Glashow. So their theory was based on a kind of symmetry, a symmetry that we call Su5. So symmetries are a kind of mathematical structure where if you change something, something is left unchanged. So if I take a perfect sphere and I rotate it, the shape of that object doesn't change. That's because it has a rotational symmetry. That's the sphere intrinsically has a rotational symmetry. When we talk about the symmetries of particle physics, we're usually meaning that different kinds of states or different kinds of particles are really different versions of each other. So for example, the weak force can transform the electron into the neutrino. That's because the symmetries of the Standard Model say that the electron and neutrino are really different states of the same underlying thing. The symmetries of the Standard Model also say that there are 8 different gluons, and those particles can be thought of as different states of the same underlying thing. So there are different symmetries built into the Standard Model, and the symmetry of Su5 is a single symmetry that takes all those symmetries and kind of combines them into a simpler and more elegant structure. It relates all of the things that the Standard Model relates to each other, and it relates things in a even more overarching way, including relating the photons to the gluons and the leptons to the quarks and so on and so forth in this one coherent package. So it turns out that the symmetry Su5 is the simplest symmetry that includes all of the features we know about in the Standard Model. This means that symmetry, the Su5 symmetry, if you look at it, it says that there have to exist things like the photon, the various gluons, the W and Z bosons, all these things that are part of the Standard Model are intrinsically included in the Su5 symmetry. So in the Standard Model, it turns out there's not just one gluon, but there are 8 different kinds of gluons. These are all these particles that communicate the strong force, and the different gluons carry different amounts or different kinds of color, this charge we call color. In this Su5 grand unified theory, all of these particles, the photon, the 8 gluons, the W and Z bosons, all of them are different states of the same underlying thing, just like those 8 gluons are really different states of the same underlying particle that communicates a strong force. Furthermore, it turns out that in the simplest version of that SU5, what we call the simplest representations of SU5, it automatically predicts exactly the right kinds of quarks and leptons, the matter particles that we find in the standard model. It explains things like why there's an electron, why there's a neutrino, why the quarks look the way they do. All of that is built into the symmetries of SU5. So you can begin to see why this relatively simple idea, this one symmetry we start with, is so attractive because it starts to explain everything we know about the standard model, or at least a lot of what we know about the standard model. So if there were a perfect grand unified theory, one that wasn't broken or the symmetry was fully intact, we would expect all three of the forces in the standard model to be exactly equal in their strength. And they're not. When we go out in particle accelerators like the Large Hadron Collider and others, we find that the strong nuclear force is much stronger than the other two. I mean, that's why we call it the strong nuclear force. And then the weak and electromagnetic forces are comparatively feeble. But we also know, using the theory of the standard model, that as you look at that theory at higher and higher temperatures or greater energies, the strengths of those three forces will begin to evolve. And if you do that at higher and higher temperatures, you find that slowly the strong force gets a little weaker and the other two forces get a little stronger. And if you follow these far enough to a high enough temperature or energy, we find that all three of them meet at about 10 to the 15 GeV. So this is an enormous amount of energy. This is 1 trillion times higher energy than a Large Hadron Collider can study. And it was a state that our universe was in only for a very brief period of time shortly after the Big Bang. But we think that that was the kind of conditions under which these forces would all behave in the same way, and our universe would really fall under a neat, unbroken grand unified theory.
So let me just jump in to say that to actually test a grand unified theory, we'd have to build a particle collider that is way more powerful than the Large Hadron Collider in order to be able to simulate the sorts of interactions that were going on in that period of cosmic history. But at this point, this kind of collider seems pretty impossible to build.
Yeah, I mean, it would be really hard. I mean, if you wanted to build a particle accelerator that was able to collide particles at the kind of energies where the grand unified theory would kick in, it would have to be the size of the solar system.
So if building a collider this big is out of the question for the foreseeable future, are there any other ways that we could get evidence of these grand unified theories?
Yeah, so this very high grand unified scale, this 10 to the 15 GeV or so, we expect there in a grand unified theory to be a bunch of particles up there, including ones that can, interact with particles in ways that we've never seen. Specifically, these particles should be able to transform quarks into leptons and vice versa. And one facet of that, or one prediction of that, is that it should be able to cause protons to decay. After all, protons are made up of quarks, and if you could take a quark and a proton and turn it into a lepton, it would cause that whole proton just to dissolve into lighter particles like mesons and electrons, but just lighter forms of matter and energy. And fortunately, we don't see protons dissolving around us all the time. That would be bad for our world. But that's okay with grand unified theories. In fact, the simplest SU5 model that we've been talking about predicts that protons should have a half-life of about 10 to the 31 years, which is way longer than the age of the universe. So it seems like protons are pretty safe. But that doesn't mean we can't test this. If we look at enough protons at the same time, let's say you look at 10 to the 31 protons for a year and you don't see any of them decay, that allows you to test this kind of theory. And over the last, couple of decades or few decades, people have looked for proton decay with really high levels of precision, and they haven't seen any. The current constraints are, 10 to the 34 years or so using an experiment called Supersymmetry. So these simplest grand unified theories, like the SU5 one we've been talking about, that seems to be ruled out by the fact that protons don't decay as fast as they predict.
But are there more complicated theories then that get around that constraint?
Yeah, so some people have advocated for even bigger and more complicated symmetries. One popular one is called SO10. It's a lot like SU5, but just bigger and includes more particles and things like that. And then the other solution is to keep the SU5, but include something we call supersymmetry. So supersymmetry, we've talked about in other episodes of this podcast, but it includes adding a whole bunch of extra particles. And if those particles really exist, then it will change how the strengths of the forces evolve with energy or temperature. And instead of predicting that the grand unification kicks in at 10 to the 15 GeV, it predicts that they'll kick in at about 10 to the 16 GeV instead. And therefore, those particles that can make protons decay are even heavier and less efficient. And it explains why protons live longer than we've seen, as long as they seem to. In these kind of simplest SU5, in these simplest SU5 grand unified theories that include supersymmetry, the proton should live about 10 to the 36 years or so, which is beyond the reach of any current experiment.
So I guess the caveat here is that there are reasons for physicists to be less confident in string theory than they used to be. We'll probably make a whole episode about that at one point. But I think the point is that, even without building a giant particle collider the size of the solar system, there are still ways that we can test these grand unified theories, and theorists are also coming up with ways to adjust the theory to respond to these constraints. So all in all, grand unified theories are still very viable.
Yeah, and I don't want to give you the impression that looking for proton decay at this level is easy, but it's a lot easier than trying to build a particle accelerator the size of the solar system. That's for sure. And there are some experiments that are going to be conducted in the years and decades ahead that will improve our sensitivity to proton decay. I'm really excited about these experiments. One of them is, a big deal at Fermilab where I work. It's called Dune, and it's going to be a giant underground, facility in Homestake Mine in South Dakota. And it can do a whole bunch of things with neutrinos and other sorts of science. But one of the things I'm the most excited about is that it will be able to, with even greater sensitivity, test the lifetime of the proton.
These grand unified theories, if they're true, they work to combine three forces into one. But there's a fourth force out there. There's the force of gravity, right? So how do we include that? Is there a grand unified theory that could include gravity?
Well, gravity is a really different kind of force than the other ones we've been talking about. The electromagnetic force, the strong nuclear force, and the weak nuclear force all kind of look qualitatively similar. We understand them in the same sort of framework. We use the language of quantum field theory to talk about it. And those features make it a lot easier to figure out how they would fit together into a single theoretical framework. Gravity is a different thing. We use the theory of general relativity, which isn't a quantum theory at all. We don't know how particles communicate gravity through space. We don't have a theory of quantum gravity, and therefore we really don't know how we would try to connect this with the other forces. There are lots of ideas like string theory and loop quantum gravity, but frankly, we don't know if those have anything to do with nature or not. They're maybe our best guess, but we just don't know. A point of nomenclature is when we talk about a grand unified theory, we're talking about combining those three forces we've been talking about. When we talk about combining those forces with gravity, we give it an even grander name. We call those theories of everything, which sounds really presumptive, but that would ultimately be the perfect all-encompassing theory that explains absolutely everything there is about our universe, all the forces, all the types of matter and energy, space and time themselves, all of it wrapped up into a profound and pinnacle of human history sort of theory.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.